Okay, let's go ahead and get started with class 5. Today we're going to talk about C language data types. And when we talk about data types here, we've seen in the past data types used for both variables and data types used for defining parameters to go to functions and return values from functions. So we're referring to any of those data types there. And to get started on this, the first thing is C language has this kind of small but powerful set of data types available. And those can be organized into 3 different categories. The scalar types, which are kind of numeric values, like 1, 2, 3, or it could be even floating point numeric values like 1.5, 1.501. But notice that the thing about scalar types is they hold one single value, and they can be compared to which one's greater, are they equal, and so forth, so you can compare their magnitude. The second classification is aggregate types, and that would be groups of things stored together, which could be structures, which we haven't talked about yet, but we will later, unions and arrays. We're going to not focus on those today. We'll come back to that later. There's some concepts we have to learn before we can understand aggregate types and use them. And then there's a special type in C called the void type. And we'll see that later on in the semester as well. So today what I want to focus on are these scalar types, the typical variable types that you'd be used to having. Okay, so looking at those scalar variables and the types associated with them, a variable has to be declared before it can be used. So you can't do like you do in Python, where just on the fly you want a variable and you say like x equal 5 and now you have a new variable. You can't do that. You have to declare them before you use them. And so an example would be somewhere in your code, if you want to have an integer variable I, you'd have to say int I. So that you notice there's no def, there's no define. You just say int and then give it the name of the variable you want. You can also declare multiple variables on separate lines, or you could declare 2 of them on one line, like int a comma b or int I comma j. So you can declare multiple variables on one line as long as they have the same type with the same type specifier. So the general form for that is the type that you want, and then some white space, and then the name that you want for that variable. Now, it's important to note here that the names for variables are the same as the names for other identifiers in C, meaning it has to start with an underscore or a letter, and it can only consist of underscores, letters, and digits. And so you could have a variable name that is just underscore or underscore underscore or underscore I or underscore 5. All of those are okay. But you could not have a variable name that was like the digit 5 guys or something like that. So it would have to start with a letter or digit. Now, there are 5 basic scalar types: char, int, float, double, and enum. Sometimes people call these chars, but this char is a character variable. We'll talk about that in a little bit. And those types have this ability to further be qualified for some of them, and some of them qualified in other ways. Now, there are 4 additional qualifiers: short, long, signed, and unsigned. And it's important to note that short and long, these first 2, and signed and unsigned, those can all be used with the int type. So notice that gives us you can't do long and short together. You can't do signed and unsigned together. These are kind of like selectors or qualifiers. So notice that with 2 here and 2 there, that gives us 4 possibilities to go with that int type. You could have a short signed int, you could have a short unsigned int, you could have a long signed int, and a long unsigned int. And if you leave off those all together, it'll use this default behavior, which we'll talk about in a second. And notice that if you're dealing with modifying or qualifying the character type, the char type, then it can only be signed or unsigned. There is no short char or long char associated with the character type. Okay, so that in strict ANSI C89, all variables have to also be declared at not just before they're used, but at the top of an executable block of code. So in other words, if you had a function that you defined, and here's the function body, you would put all of the variables, the local variables that function uses, at the top of that block of code. Now that was later relaxed for the C99 standard and later, where you could declare a variable on the fly inside of another code block somewhere else inside of your, like you make a for loop and you want a temporary variable, you can put it right inside there and then use it inside there. But if you wanted something to be backwards compatible all the way back to C89, declare all your variables at the top. And that can also be not a bad practice to get into, because when you look at a function, you can see all the variables that are being used in there. There are cases there where that can be problematic. If you have a really large function and you're only using a variable way at the bottom of it, why declare it at the top and then have to search for that at the top when you want to look at what type it is or something like that. All right, one important thing to note, though, is looking at these examples here. Here's a type, char. There's the name of the variable c. We could make a signed char or an unsigned char. And notice the difference between those is the char by itself. In most compilers, that will become a signed character by default, and it'll be signed by default. And notice really that it's a char type is just a single byte or 8-bit integer type. It doesn't have anything to do really with characters or strings or anything like that. In fact, there is no string type in C. We can still do stuff with strings, but we don't do it with its own special type. We'll look at that later in the semester. But notice that the difference here is with the signed version of a character, the range of values goes from -128 to 127. In other words, we still have 256 possible combinations, but the way they're treated in a signed form is here are the 8 bits. The most significant bit is, and I'm doing this in reverse, the most significant bit, which is all the way over here, is the signed bit. If it's 0, it's positive. If it's 1, it's negative. And then since there's no such thing as a -0, they've shifted all the negative range down by 1. So it goes from -128 to 127. Now the unsigned version of a character variable, all 8 bits, range from 0 at the smallest to 255 at the highest, with all of those switches turned on. So the range of values, 0 to 255. And so you'll notice that that character type is really just a single byte integer type. That's all that it is. So it's 1 byte, 1 8-bit block of memory that's associated with that name that we gave it. In this case, C. And notice if I make it signed, that's interpreted a little bit differently than it is if we make it unsigned. Okay, int. If you say int I in your code, that's going to create an integer variable named I. And int is going to be maybe a 16-bit value, maybe a 32-bit value. Let me actually edit this real quick and change this. And the reason why that's not specified is they left it up to the compiler for the system to use whatever the most natural native type is. So if you just say int I, on some compilers you'll get a 16-bit value. On some compilers you'll get a 32-bit value. So it might be either short or long. Now what does short and long mean? A short int is going to be the 16-bit storage. A long int, as we'll see in a little bit, is going to be a 32-bit value. But now one of the things to notice is look at all the ways you can create this short int. You can say short int I, you can say short I, signed short, signed short int. So really, what they've done is they made it so if you use one of the qualifiers, and actually I left off one, you could just say signed I and leave off the short, and then it would have 16-bit or 32 and do that. But notice you can kind of leave off the int part if you're using the qualifiers. And that can be confusing if you haven't seen code. You come across things like short I. That's the same as saying short int. It's just a shorter, less typing in order to get the same thing. Now, one of the other things is by default, int values are always going to be signed, but you can specify signed in your code if you want to. So notice that all 4 of these things that we put up here produce the same kind of variable. If I say short int or signed short int, I get the same kind of variable. It's going to be a signed short integer that can hold a value in the range -32,768 all the way up through 32,767. Now, if I make one of those unsigned, and say unsigned short int, or unsigned short I, then I get a range 0 to 65,535. And again, that's 16 bits rather than 8 bits worth of storage. And so note that I have that note at the bottom. It says all of the above produce a signed 16-bit, I shouldn't say signed there. It should just say, let me fix that one here too. The first 4 produce a signed value. The other ones don't. But the int type, by default, it could be 16-bit or 32. So on the compilers that we're going to be using in this class, code blocks, using GCC, you're going to get a 32-bit int when you say int. But if you move that code to a microcontroller or something else that's running on an 8-bit or a 16-bit microcontroller, or even if you're just using a different compiler, it might, int by itself, might produce a 16-bit value. Now, one interesting thing is that the default is always signed. So if you don't specify signed or unsigned, you're always going to get signed. But if you don't specify short or long, on GCC, you're going to get long. On another compiler, you might get long. On other ones, you might get short. So to be safe, if it matters that it's short or long, specify short or long. And we'll talk about that more in just a minute. Okay, for long variables, those are 32-bit values. So a long int or long I, or so long or long int, both produce values in this range. Signed long int, signed long produce the same thing. So notice these 4 top things all do the same thing. But you can also specify unsigned. And you'll notice that the range of values there for unsigned goes from 0 up to 2 to the 32 minus 1, which is going to be 4.29 million, whatever, what's that, million? Billion. 4.29 billion, whatever it comes to. But the idea is the same as with the character variable. In other words, we're taking those 32 bits, same as with a short also, taking those 32 bits, the most significant bit of those is going to become the signed bit, and then the rest of them become the digit portion of that, whether it's negative or positive. And it's a little bit more complicated than that because the negative numbers use what's called 2's complement, where it's the inverse of the bit pattern and then it's shifted by 1 to avoid that case where you'd have a negative 0. So it's shifted downwards by 1, which is why this goes to 21474833648, and this goes to 7. That's because the negative range is shifted down by 1. Now, those are the integer types supported by the C89 ANSI standards. And there are some additional types that were added in C99 and later. There's also a bool type that was added later for booleans, true or false. We're not going to talk about that right now. We'll come back to that later on, but I do want to mention this type. There's a type called long, which is a 64-bit integer value. And the way you would declare those is to say long int, or just long, or signed long, or signed long int, or unsigned long, or unsigned long int. And you'll notice that there's a signed version and an unsigned version. There's just multiple ways of specifying that. And those were added in C99. It's standard in C99 and later, so you can use those on the compiler we're using in here. But that long type is essentially just a 64-bit value. And again, the signed version, the most significant bit, acts as the signed bit, and then it's shifted toward the negative range by 1. So negative 263 to positive 2 to the 63 to positive 2 to the 63 minus 1. And if it's the unsigned version, 0 to 2 to the 64 minus 1. And the reason for the minus 1 on this positive end is, remember, we have to represent 0. So it's 1 less than the number of combinations, because one of those combinations has to be used for 0. Okay, now moving on to things that are not integer values. Notice you can also store floating point values, things that have decimal points in them. And the floating point value here, notice that if I say float f, float becomes the name of the type. And that's a 32-bit worth of storage, IEEE 754 single precision value. And the way that's stored internally doesn't really matter a whole lot to us right now, but it might at some point. But notice that it has 32 bits, and that those are color coded here: green, red, yellow, purple. And it has a sign bit at the very top. So the sign bit is the most significant bit, and then the next 8 bits after that are the exponent, which essentially what the exponent is doing is how far do we move the decimal point, either left or right. And then we have the next 23 bits are the actual digit portion of it. And one of the things about that digit portion is it's actually 24 bits, even though there's only 23 in the message. And that's because the most significant bit is always assumed to be a 1 in that case. So if there's a 1 in that most significant position, assumed that there's a 1 there, and then it shifts all of it around with that 1. So it's assumed there's at least a 1. The only case where that doesn't happen is when you have a representing 0. We don't want to worry too much about the details of this right now. But a couple things to notice is that there is no signed or unsigned version. There is no long or short version of a float. It's just a float. And that's governed by this different standard that's IEEE 754, which is a kind of the document that describes how to store floating point values in computer systems. But I did put a couple examples over here. So positive 10 looks like this in memory. So if you were to write out the bit pattern for these, 4. So positive, we know the most significant bits are going to be 0. So 0, 1, 0, 0. And then 1, 0, 0, 0, 1. And that's the end of that. And then 2, so 0, 0, 1, 0. And then all the rest of these are zeros. And that's what a 10 looks like. And negative 100 looks like this. This thing close to pi. Positive 3.1416 looks like that in memory. Minus 1.25 looks like that. But really, it's just placing the pattern of bits in there to say this is the digits. This is where the decimal point gets moved in those digits. And then it's positive or it's negative. Now, one thing that's important to note is with single precision, you get about 7.2 decimal digits of accuracy. In other words, if you wanted to represent a number that had more than 7 digits of accuracy, decimal digits of accuracy, then you need something other than a float. So in other words, you could represent something like 1.000, so 1.00000, we're up to 6, 1. But you couldn't do 0.0001 because you would lose that precision there. And that's something to watch out for when you're writing code, is that there's a floating point error that can happen, where if you have a number with a really small fractional parts and you're using that in arithmetic operations, some of that precision can get lost because the bit pattern only has so many digits worth of accuracy that it can store before they get lost. So you got to be a little bit careful. Now, there are some types that have more precision. Let's look at those. There's one called double. And a double is twice as much storage, so a 64-bit double precision value. And what that does is it stores things the same way. It still has a sign bit, but now it has 11 exponent bits and 52 positions for digits. So essentially what this is, it works the same way, but it's single precision, but it gives more precision worth of digits. And in this case, it's 15 to 17 decimal digits worth of precision. 15, if you, as a guarantee, you'll have a little bit, 15.4 something digits worth of precision as the worst case. So now you can store things that have a total of 15 decimal digits and then place the decimal point somewhere in there. And we'll come back and see a little more with these in a second. Now, there is one other type, the long double. On most systems, that's an 80-bit, what's called an extended precision floating point value. I think that's what it is on the GCC compiler that we're using and on other x86 compilers. But on some compilers, it's actually a 128-bit floating point value. But let's focus on what we're using this for. So essentially the 80-bit value gives 18 decimal digits worth of precision. So that long double doesn't necessarily jump to 128 bits with 31 digits worth of precision. On most x86 compilers in Windows or something like that, you'll get the 80-bit extended precision format. And just for comparison, here are the three formats. There's the float. You can see the exponent portion, the decimal digit portion, and then the signed bit. They all work the same way. The only difference is when you go up there, add additional exponent bits and additional digit bits. I don't have the 128-bit one on there, but that looks essentially like a doubled version of this one. So double the exponent, double the digits, much more data. Now the question would be, why do you care about which one of these you use? Why not just use long double for everything? But keep in mind that it's slower for the processor to have to do arithmetic on these larger numbers of bits than on a smaller number of bits, and it also takes up more memory in the computer when you're using these other larger types. So there are cases where you'd want to use the float version of this because it's going to be faster. There are cases where you might want to use double or long double where you need more precision. But it's up to you to figure out which of those types you want to use. It won't automatically like make the type bigger when you get to more precision. Essentially, if you make a variable and make it a float, you're stuck with it being a float until that part of the code finishes. All right, now as a quick summary here of all those scalar variables, we started off with a char, which is 1 byte. Unsigned char is also 1 byte, just interprets the range a little bit different. Short is 2, unsigned short is also 2, long is 4, unsigned long, and these are ints here. Float is 4, but it's interpreted differently than the long. It's not an integer, it's interpreted this way. Notice that you can get from 3.4 times 10 to the negative 38 all the way up to 3.4 times 10 to the positive 38, which allows for some really small or really big numbers. But keep in mind that you only have that 7.2 decimal digits worth of precision there. So even though you can have a number with 3.4 something with 38 zero, the decimal place moved 38 points to the left or to the right, remember that you only have 7.2 digits worth of precision there. And notice that when you go to a double, we go 1.7 times e to the negative 308. So that's a really tiny number. Imagine moving that decimal point either to the left or the right 308 positions. But again, now we're up to 15 digits worth of accuracy. And then the long double is a 10 byte, again 80-bit usually. So 3.4 times 10 to the either negative 4,932 or 1.1 e 4932 in the positive direction. And you'll notice a little bit of asymmetry in those ones. And then over on the side here, this format string, that's if you're going to be printing these out using a printf, like %d we did for integer, which notice is up here, %d, to print out an integer. You'll need to use these for different things. So we'll talk about that a little more later on in the class, but those are just on there if you want to look at them. Now, again, an int when used by itself might be a 16 or a 32. In some cases, it might even be 64 bits. It just uses the native size of the compiler for the architecture it's on. So just be cautious if you make an int variable and that code might not be completely portable. You might get a different size for that variable on a microcontroller that you would on a PC. Or if you use a different compiler on one platform, one of them might be a 16-bit int, one might make a 32-bit int. And the reason for that is the standard only specifies the minimum sizes for things like int. And so since it doesn't really specify, to be safe, always use short and long when dealing with int types. And I'm not going to, in this class, I'm probably going to write sample code that doesn't always use short and long. But just note that if you're writing production code, you want it to be portable or need it to be portable, use short and long to specify, so because just int by itself leaves it up to the compiler to use whatever the native for it is. As far as signed and unsigned, the default is always signed. So if you want something unsigned, specify. If you don't, then you can leave it off. But again, to be safe, specify. And for clarity of your code, there's actually another way to specify these rather than using the original C language types, which there's a set of C99 typedefs. We're going to look at that toward the end of today's lecture. Okay, numeric constants. Numeric constants are essentially things you put in your code to specify a number. And there's several ways to do that. One of them would be just use the number. Like here I use an integer 65 to stick it into this character variable ch. You can also use a character in single quotes that will automatically provide the ASCII value of that character for you and put it in there. And you can also use hex constants in your code. So note that all three of these examples here end up putting the number 65 into that single byte of memory associated with this variable ch. Now, I do want to mention this, that C, being a systems programming language, when you create a variable like this, char ch, there's no like table being stored. It's not some dynamic thing in like a virtual machine like it is in Python or an interpreter like in Python. This is actually saying, take a byte of memory, a single byte of memory, and when we refer to this variable ch, we're going to refer to that single byte of memory. We're going to access that single byte of memory. So when I say char ch, that's creating this variable, which is a single byte in memory. And when I say ch equals 65, that's essentially moving the number 65 into that byte of memory. So there's very little overhead. It's directly mapping these variables onto bytes of memory stored in that memory map of the machine. And it's up to us in our code. We could say ch equals 65. That'll have the same effect and generate the same executable code that this will, which will generate the same executable code this will. There's no difference in the actual, what the processor does for any of these three. It's just up to us whether we want to specify it as an integer or a character constant. And remember, use single quotes for that. Or whether we want to use a hex constant. There's also another one called an octal constant that we'll see here in a second. But also because of that, notice I can use these characters in an arithmetic context. I can say capital B minus capital A. And essentially what the code that's going to get generated is going to be 66 minus 65. And I'm going to get the number 1 put into ch here. You can also take this character variable ch and do arithmetic operations upon it, perform those. So here's ch plus 1. If we put a 65 in there, or in this case 1, and we did ch plus 1 and then put that back in there, we've now changed it to a 2. So again, a character type has nothing to do with like characters or strings or stuff like you usually think of it as just a single byte, an 8-bit integer type, single 8-bit integer byte type of memory. All right, so back to the constants, decimal constants, base 10, just type in the numbers. Hexadecimal constants, just prefix them with 0x. And it doesn't matter if they're uppercase or lowercase a through f. Also notice you can do negative hexadecimal numbers just fine. And also notice now we have these octal constants, which are base 8. And you probably won't see those a whole lot, but they'll be encoded in that. You prefix a constant with a 0, and it becomes octal. So just watch for those. So in other words, 003 is not the same. Well, in this case, it would be the same as 3 in that. But 010 is not the same as 10. It's the same as 8. So just watch for that in the code. Don't think the leading zeros are just zeros. That actually changes it to an octal constant, which is base 8. And the real difference between hex and octal is base 8 is in blocks of 3 bits. So in other words, this 377, you can kind of visualize that as this lower least significant 7 is 3 bits. The next one is 3 bits, and then the top one is 2 bits, which is 11, 111, 111, or the same as 0xff here. Okay, now those constants support suffixes to change them from signed to unsigned, or from short to long. And you can specify that by putting this at the end. So some examples down here. If you stick a U at the end, that becomes unsigned. If you stick an L at the end, it becomes long. If you stick an L and a U at the end, it becomes a long unsigned constant. All right, for floating point constants, you just put anything with a decimal point somewhere in it. You don't have to have something before the decimal point. You don't have to have something after it. So 3 point is the same as 3.0. 0.7 is the same as 0.7, or you can specify stuff before and after the decimal point. And one of the things, by default, all floating point constants use double precision. That can generate some code that is not necessarily optimized, so they gave us a suffix to specify, don't make this constant double precision, and you just put a lowercase f after it. So if I say 3.5f, that'll give me a single precision 32-bit floating point constant. If I were to just say 3.5 in my code, I would get a 64-bit double precision constant. So that defaults to higher precision for safety reasons, but you can override that for efficiency by putting that f on the end. Also note that scientific notation is supported, so I can say like 3e2 is the same as 300, or 2.5e negative 4 will give me 0.00025. So note that you can use scientific notation for really large numbers or really small numbers, however you'd like. Oops. Whoa, hold on. All right, there we are. All right, so one of the things that comes up though is like, what happens if we mix two types? Well, if I mix an integer with a floating point number, like we have up here, what happens? And so C allows that, but the way it works is it says this is an integer. This, in our case, we didn't put an F, so this is going to be a double. So what do I do when I have an integer and a double? Well, those are stored differently in memory. The bit patterns are different. So what the compiler does is it's smart enough, rather than kicking out an error saying the types don't match, it'll do what's called an implicit cast, or a implicit conversion, meaning that implicit means you're implying that you want this thing converted. That's an integer. This is a double. Something has to get converted in order to do that. So which way does it convert? Well, it'll automatically convert from the lower precision type to the higher precision type. And there are rules for how it does that cast from one type to another. And we're going to look at that in a second. But in other words, we want to look at every one of these operations that happen in the order they happen, and then say if the types are different, one of them has to be converted. And let's just take a look at the rules. So here are the typecast rules. The rules are character types are automatically cast to int in expression. So anywhere you have a character type in an expression, it's automatically converted into a 32-bit or 16-bit int type, depending on the compiler you're on. If you have the same type between a single operation, like this divided by this or this times this, if they're the same type, the result of the operation will be the type of each of those two. So that same type does not produce a cast to get a different result. So, and you'll notice back here, we said this had a problem in it. And we'll come back to that problem here in a second to look at why is that a problem. It looks like we're saying 3.0 plus 1/2 would give us 3.5. There's a problem there. We'll come back to that. And that's because of the second rule. The same type produces no conversions. All right, if they're different types, the most precise type is used. So in other words, the more precise of those two types is the one that's used. So in other words, the lower precision types are cast up to higher precision before the operation happens. And how does it know which ones are lower and which ones higher? Well, it uses this thing called the C-type hierarchy to determine the level of precision. And at the least precise end, we have just normal characters. Above that is unsigned characters, short int, unsigned short int, long int, unsigned long int, long long, unsigned long long, float, double, long double. And that's the most precise type that we have, is that long double. And again, we said this just a second ago, but I'll say it again. The result of any operation will take on the type of the more precise of the operands involved in that operation. All right, so let's look at that. So note that those rules, those implicit casting rules, can sometimes result in problems. So here's that problem we saw earlier. Num equal 3.0 plus 1 divided by 2. So 3.0 plus 1/2. So what number is in num when this completes? Well, a novice C programmer might think, well, it's going to be 3.5 because I had 3.0 and I added a half to it. But the problem comes in that this is an integer. That's an integer. We're doing an integer divided by an integer. The result is going to take on the type of the most precise, which is integer. So the result of this operation right here is going to be an integer. And that creates a problem because you can't represent 0.5 in an integer, so this results in 0. So the result of what you're going to get in num is just going to be 3.0. You're not going to get 3.5 because this is going to result in 0 because of those type rules. Down here, num equal 10u minus 15. Well, you made that unsigned. Unsigned in our type hierarchy has a higher precision than signed does. So what's going to happen here is this is going to get converted to an unsigned, and our result's going to be unsigned, which means that normally you'd say 10 minus 15, that should be -5. You're not going to get -5 out of that. You're going to get whatever the interpretation of unsigned 10, unsigned 15 converted to a signed is going to be some large number. You're going to get a large number out of this. It's unexpected. And this third one here is even more insidious because we're saying 10 divided by 1/2. Well, you'd think you'd get 20 out of that, but you won't, because this will result in 0, and you'll get a division by 0 error actually at runtime when you run this. So this could crash your program. This will just get a wrong value. This could actually crash the program. All right, so one of the things to help control that behavior that we have is, rather than just having implicit casting, you can also have explicit casting, where the programmer gets to decide when those conversions happen. Now, what explicit casting does is allows us, when we write our code, to specify when and to what type we want something converted as. And the typical way that that's done is in parentheses before something that you want converted, you just put the name of the type you want it converted as. So in this case, where I have a 2, which was an integer 2, I can make it into a float by just putting this cast in front of it. Now, normally to make it into a float, you could just say like 2.0, that would work as well. But if you had a variable that was an integer variable and you want to make it into a float, then you can just put parenthesis float in front of it, and that says, hey compiler, take this value, convert it for me before you use it. Now, notice that one way to fix that problem we had earlier, those two problems we had earlier, you just put a float cast in front of that 2. And now since I have a float 2 and an integer 1, it'll implicitly convert the 1 to 1.0. 1.0 divided by 2.0 will be 0.5. And now we get the expected value of 3.5 in there. And the same thing with 1 down here. Float 1 divided by 2. Well, that's 1.0 divided by 2. This 2 integer here has to get cast to a float. And when that becomes a float, we now have float divided by float, which results in float. So this is 0.5, so now we have 10.0 divided by 0.5 gives us 20.0 as a float. So explicit casting, essentially, the way that you do that, you place the desired type in the parentheses before the data converted, and it'll do the conversion that we request for us. And note that you can cast upwards or downwards. In other words, I could take a float value and I could force it to be an int. And in that case, it'll truncate anything after the decimal place, just throw it away. But note that you can perform that casting either upwards to make the type more precise or less type, and you can move up and down this kind of anywhere on this type hierarchy that you want. Okay, last couple things here. There are these enumeration types, which enumeration type takes a little bit of getting used to, but it's still an integer type. It's still numbers. But it's a way to represent those numbers as a set of names rather than a set of numbers themselves. So notice here, I'm creating this type, enumerated type. These are the types that I want to, or the constants I want it to have, elf, gnome, troll, human, and this is the name of the variable, race. So in my code, race can take on any one of these enumerated types, and that's it. You can't put other values in it. Even though behind the scenes it's stored as an integer, I'm using the names of these defined names instead. So I could say race equal elf, race equal gnome, race equal troll, race equal human, but that's it. I can't say anything else. Oops. And the same thing is true here for any of these. We can make any of these we want. So gender, disposition, evil, neutral, good. We could say, make a thing called character class and make like wizard or thief or warrior, whatever you want to put there. But notice that this gives us the ability to now have our code say race equal elf rather than race equals 0. But behind the scenes, note that these start at 0, 0, 1, 2, 3, 0, 1, 2, 0, 1. But notice that if we tried to set one of them, even though elf is 0 and male is 0, the compiler will not allow you to misuse one of these. So you can't say gender equal elf because that's not one of the enumerated types. It'll force it to be either that or that and not some other number. All right, so behind the scenes, those are just integers. And the main use of those enumerated types is it can make your code more readable, and it can also make it less error prone. In other words, with disposition, the only things we can assign it to would be evil, neutral, or good. In other words, we couldn't set it to a value of 4 or 8 or gnome or troll. We're stuck with it has to be one of the things that we assigned up here. And it's the compiler that's enforcing that, which means there's almost no overhead to using these. It's just like using integers, very fast, very efficient. It's not like a special class that's doing it that we had to create that's enforcing that. The compiler's enforcing it. In other words, when I say gender, we're going to get either male or we're going to get female. Or if I say disposition, we're going to get evil or neutral or good. And if we wanted to add more things and have like chaotic evil and whatever else we wanted to add to this, we could add more things to this and recompile it. The compiler will make sure we're not using it wrong, but this has to be one of the values in the enumerated type. Now, by default, they all start integer values of 0, 0, 1, 2, 3. But if you wanted to, you can actually override that. We could say, for example, evil equal 5, and then it would be 5, 6, 7. So we could actually override that and allow these to have different constants underlying it if we wanted to. In fact, you could go through and put an equal sign each one. Evil equal 1, neutral equal 2, good equal 4, and then you could treat them like bit place values if you wanted to. Okay, the last thing here, and I said we'd mention this later on when we talked about this earlier, is C allows you to define your own names for types. So in other words, there's this mechanism called a typedef. And what typedef, it's different than pound define in that we're saying, hey, when I want to define this type as this other name, and hold on one second here, I'll be right back. Okay, we're back, sorry about that. I had somebody knocking that I had to deal with. But notice that here we have this unsigned typedef unsigned int as uint. That means from that point on, rather than typing unsigned int over and over, I can just say uint a comma b and get that same thing as if I typed this whole thing out. Now, that can be useful for making your code a little more compact. It can also be useful for making the code a little more readable. Remember when we had those things like unsigned short int or unsigned long or signed long int. Notice that that's a lot of stuff to type out, so you can kind of shorten that by using typedefs. And in fact, it's so useful that in C99, the standard added some standardized defines in a file standard int.h. So if you just pound include standard int.h, then you can use these defines here that are standard. And notice the cool thing about these is they tell right in the name how many bits worth of storage it's using. So in other words, an int 8 underscore t, the underscore c stands for type. So this is an int 8 type, it's an integer that's 8. Really, this is the same as a signed character variable, but we can just say int 8t and it tells us how many bits that is. And there's one of those for the 8-bit versions, both signed and unsigned, 16-bit, 32-bit, 64-bit. And some compilers also will have typedefs that define, instead of those lengthy things, even shorter versions, like S8, U8, S16, U16, S32, U32, S64, U64. And if it doesn't have those, you could always typedef them yourself if you wanted to, and then use these. And the advantage of that, it makes it so there's no ambiguity on what platform was this integer to be used on. Because if you use these types, notice every one of them has how many bits it's actually using on it. So there's no ambiguity on an int 16 or an S16. We know it's signed. We know it's 16 bits. It makes the code more cross-platform to specify those that way. Now in class, I may do some examples that use these, but I also may use the other types so that you get used to them. But in production code, a lot of C programming style guides, they prefer that you use these, even though they're not part of the language itself. But it's still important to know how to use those other types. So in our examples, I'm going to use a lot of those other ones. The other fun thing is you can make your own typedefs and define things. Now, typedefs can also be useful later when we get into the aggregate types for things like structures and unions. We're going to see that later on. But since we made it through the scalar types today, we're going to stop there. One thing to notice was that there was no string. There were no string types anywhere in here. And the character type is really just an 8-bit integer type. So we'll talk about how strings are dealt with later on in the semester. But that's it for today. Work on finishing up your lab number 1. Everybody stay safe, wash your hands. And next class we're going to dig into C language flow control with if statements and while loops, the for loop. And then we're going to start putting things together to do that. And then we're going to have another lab. So try to finish up lab 1 because there'll be another one coming. There also may be a quiz coming up, so watch out for that. And that's it for today. And I'll see you guys next time.